Thank you very much for that introduction. Many of you, may not know me, but you probably are aware of my colleague, GP, who I work with closely. In fact, our offices just moved into GP's building about a month ago, so we actually see each other every day. GP has really worked tremendously hard to build an impressive infrastructure and hardware to do cutting-edge technology research. And I feel lucky to now be able to take advantage of that infrastructure and essentially try to build tools for clinical artificial intelligence with that foundation he laid. So that's a little background on me. I'm going to talk a little bit today about artificial intelligence and the implementations in clinical practice, specifically at our hospital. The outline is very simple, so I'm going to cover a very brief introduction about artificial intelligence and deep learning. We've heard about it numerous times throughout this entire conference, so I don't think it really needs that much of an introduction. And then I'll spend most of the time describing some of the opportunities and specifically highlight the tools that we've created at our hospital, which we've sort of tested out and tried in practice. So that'll be the overview. In terms of a background on deep learning, again, this is probably not news to you, but I just really want to highlight a few key points about the technology. One is the fact that deep learning is in fact very new, in terms of its implementation. We've described it for many years now, but we really haven't seen practical applications of the technology until about 5 years ago. So really just in the blink of an eye. The novelty of the algorithm itself is that rather than needing me as a human to write rules or to program explicit logic into the algorithm, what I do as a developer is to simply create a virtual network of neurons, a virtual brain, if you will, and simply give that brain the capacity to reorganize, to strengthen some of its connections and to weaken some of the connections over time. And naturally, through that process alone, intelligent behavior arises, right? I don't have to tell the algorithm anything special. Visually, what that means is if I had to write a traditional machine learning algorithm to understand what a dog looks like, traditionally, I may have needed to first break down the appearance of a dog into its components. So I look for a tail, or I look for a paw, or fur, or ears, right? I would have to come up with those rules on my own. With deep learning, all I need to do is simply tell the system that this is a dog. And whatever you want to use to figure out that this image and these set of images contain dogs is completely up to the system itself, right? So you have remarkable flexibility. And these algorithms have now far exceeded the state of the art. They're well considered to be the best performing algorithm for many of these type of tasks. Again, what this means is that rather than having myself as a programmer or a team of scientists really think hard to come up with the right mathematical equations, everything is done automatically by the deep learning system. All right, so what is possible with neural networks? What's possible with deep learning? Well, I'm going to start here with a video. This is a tool, a system that we've created at our hospital to evaluate for the presence of a bleed in the brain, so on a non-contrast head CT exam. This tool actually runs live in our hospital, so every patient that comes into our emergency room with a suspected head trauma gets evaluated by the AI system in parallel. As you can see in real time, as a new patient is being scanned, the algorithm is immediately scanning through the images and trying to look for a particular abnormality. A case of positive hemorrhage is notified with a little red dot, and through the same interface, if you scroll down through the images, you'll see that indeed, right in the brainstem there's a bright area indicating hemorrhage, and with the click of a button, that volume of hemorrhage can be outlined for you. So that's one example of a system. I'm going to go through many, but I just want you to think about that in the back of your mind as we talk about sort of designing and thinking about these algorithms. So how did we get there? Well, it turns out while there's many things that AI can solve, there are practically some limitations and some considerations we need to think about. These considerations include technology. So what can we solve with AI given the current state of the tools? 2 is data, right? So do you have enough data or the correct kind of data to answer your question? And finally, we'll talk a little bit about the regulatory type of hurdles. Starting with the technology itself, again, while it's feasible to spend a lot of time to customize and create a very special algorithm to do very complicated things, the reality is that the AI tools right now are best suited for applications that are an instinctive type of interpretation perception process, right? What that means to me as a radiologist is that if I look at an image and I can see the finding within a second, it's a reactive type of process, then that's an application that's very well suited for AI today. If I have to look at that image and think a little bit and kind of synthesize multiple different perceptions on the image, that's certainly something I do often. Those applications are much more difficult to solve. Visually, what I have here is the MNIST dataset. It's a very popular dataset of handwritten digits that introductory data scientists will use to learn how to develop these tools. If the data is clean and cropped and centered, like it is here on the right-hand side, that's a data set that we could do a workshop together and I can teach you how to make that in several hours with very, very high accuracy. If all I do is simply take that data set and start to shift around the digits, maybe add some distractors, right, make the problem just a little bit more messy, this data set is now infinitely more difficult to solve than this original one on the right. Okay, so that's just one example. In terms of data, you guys have probably heard this before, but the new wave of deep learning technology is really at its heart a big data problem, right? So we tend to need many, many examples of a disease process to properly train the top performing models that we see. These are a few examples of data sets I've worked on within the past year. So as you can see, the number of exams is in the thousands to tens or hundreds of thousands of cases. Now, initially you might be worried and think that, you know, I don't have access to this type of data. How is it possible that we can train these algorithms? Well, the fortunate part is that while today it's still a little bit challenging to get this type of data set curated, many of these data sets are being released publicly. So in the United States, these are several of the organizations, and most of these exams can actually be accessed for free by anybody, right? So you just write the organization and ask for access, and they'll give it to you. So I think this is going to become less and less of a bottleneck in the coming years. And finally, I want to touch very briefly on the regulatory approval process. It turns out that even if I have a great problem that is easy to solve and I have a lot of data for it, if I don't have an easy way to approve that model for use in clinical practice, you don't see it, right? It's not something that we use. And so in the US, we have multiple different categories, but there's been a new regulatory pathway, computer-aided triage, I've highlighted in red, that has just been created in the past year. This pathway allows an algorithm simply to go through a list of patients and identify which patients need to be read first. So which patients have a positive finding that needs to be attended to by a physician. Now, it's actually a very nice category because at the end of the day, a physician still needs to look at every image on the exam, right? So there's nothing that a human absolutely does not need to look at. And furthermore, the algorithm does not diagnose or mark up the images in any way, right? So it simply tells you that this patient needs to be interpreted first. The reason I describe this pathway is that it's actually very easy in the US to get this type of approval because you're not claiming the algorithm can do many complicated things. In fact, I would say there's probably been 10 to 12 tools in just the past year alone that have all been cleared in the US through this pathway. And so this is a very common type of question these algorithms solve, and we'll see a few of those examples here. Okay, so in the next half of this talk, I'm going to now go through some specific examples of tools we've created and that we test and use in our hospital. And again, rather than covering every possible tool, because there's too many, I'm going to characterize and categorize these opportunities in a few key themes. So we'll go through them one by one here. The first category of tools is, again, this idea of prioritized interpretation. So the triage pathway I just talked about. These applications don't necessarily represent a very challenging thing for me as a radiologist to look at, right? These are actually very easy to see. But the reality is I may need to sift through 10 or 50 or 100 patients before I can find the positive ones, right? So it does still take me a long time to make the diagnosis, and so this process simply makes my workflow better, more efficient. One example of this tool, like you saw in the video, is the detection of hemorrhage or blood in the brain. This is the first thing that you need to evaluate for when a patient comes in for either a stroke or a trauma, because it directly influences what type of treatment pathway the patient may qualify for. The algorithm we've created is it's a MASCAR CNN architecture, which I can talk about for any of the technical guys in the audience afterwards. But suffice it to say, the algorithm is, first of all, very sensitive. So we can detect hemorrhages that are less than 1 millimeter or 1 cc in volume, so little tiny subarachnoid or subtle hemorrhages. And the second thing you'll notice is that the algorithm is actually able to tell me as a physician not only what it thinks is a hemorrhage, as you see in the green boxes, but also areas that were initially suspicious, right? The algorithm had to look at a little bit longer than normal, but ultimately decided was not a true area of blood in the red, right? So it really gives me feedback as a radiologist to tell me what the AI was thinking when it made a decision, right? And that's a very important theme we'll talk about. This is another example of a tool to detect for a occlusion in the blood vessels of the brain. So one of the most common types of stroke is when a large vessel right at the brain's surface there gets occluded, as you see in the green box. This type of stroke has a very special type of treatment that the patients qualify for. And so the ability to quickly identify something like this is also very valuable. The second category of tools I'm going to talk about is the precise and reproducible measurement of some type of disease process, so disease quantification. The most common examples here are tools to measure the volume or the amount of some entity, whether it's a normal kidney, as you see here in the purple box, or a kidney with a big cancer. So this is two examples of patients with kidney cancer. The tool is not only able to tell you the total amount of tissue present on each side of the body, but also specifically outline the amount of tumor itself. So identify the cancer and tell the physician exactly how much needs to be treated. This tool is also commonly applied all over the body. Here's an example for brain tumors, doing the same kind of thing, looking, detecting the brain cancer, and then telling you exactly how much volume is present. This is very valuable both for following a patient over time and assessing how they're responding to therapy, as well as planning for certain types of specific therapy like surgery or radiation, where the boundaries of the tumor are very important for the planning process. Okay, the third category I'll go into is the objective evaluation of a finding. So quantifying something on the image that's more than just volume, right? So what's an example of something I might want to quantify with more reproducibility? Well, in the case of a stroke, a patient that comes in with an ischemic stroke, what I as a radiologist really am thinking about as I look at the images is this area of the brain just a little too dark, right? Too low attenuation, or maybe is there just a little bit too much mass effect? Now the finding is very subtle, so it's very hard for a human to even make this diagnosis. But this is something that an AI system is actually able to do very precisely, right? It's able to find a particular questioned area of abnormality and then very explicitly tell you on the scale of hundreds of thousands of patients it's seen, how dark really is this area of the brain and how much mass effect is really there, right? And these type of evaluations can be fed directly into scoring systems to estimate the amount of infarct tissue and again, affect ultimate patient therapy. The same type of precise and objective quantification is common in many types of cancers. So we have, as humans, rules and scoring systems that we've created that try to very carefully delineate different categories, but radiologists rarely agree with each other, even when the rules are very clear. And so we've developed AI systems to actually do this part automatically. So they first go through, and this is an example of prostate cancer. They go through and detect the potential areas of prostate cancer, and for every lesion, it gives it a scoring system on the continuum of PIRAD, so that's our physician scoring system, and evaluates the cancer very precisely. All right, another category that's very popular, not on the image interpretation side, but now on the image pre-processing side of things, so before the images get to a radiologist, is the idea of image reconstruction, right, or pre-processing. One example here is in the creation of images for MRI exams. It turns out that oftentimes we want to find creative ways to speed up the overall exam process, make the patient stay in the scanner shorter. The problem is typically when you do that, you don't acquire all the data. And so the images you get when you don't acquire all the data is kind of blurry, as you see right here in the middle. But using AI, having seen many, many normal patients in the past, the system can actually go in and fill in all that missing data in the original case space and smooth out your image to the one you see on the right. So that actually helps us tremendously increase the throughput of our machines and again, decrease the overall amount of time needed to make an image. Here's another example in stroke. In case you can't tell, I'm a neuroradiologist, so these are some of the tools I use the most. We currently acquire a type of CT examination, a perfusion examination, where we try to infer through calculations how much tissue is dead. But in fact, we have the exact amount of infarcted dead tissue on subsequent future exams. So why not train an AI algorithm to predict that from the original perfusion? That's what we've done here. The AI system is able to go through, look at how blood is flowing in different parts of the brain, and predict the amount of dead tissue that's already present. All right, so this is my last category of activities here. It's in the category of discovery. So I've shown examples of using an AI to find a disease that I as a human already sort of understand how to detect. This is now an example of using the AI system to teach me something I don't know. All right, so in this example, we were first interested in teaching an AI how to predict the mutations that are present in brain tumors just by looking at the images. And the algorithm itself was very accurate. It could tell you that the brain tumor had an IDH mutation or a 1p19 deletion with high accuracy. But more importantly, what we were more interested in was after the algorithm had seen thousands and thousands of brain tumors, could it tell me why it thought that there was a mutation present? And so what we were able to do here after the algorithm had finished learning is create an atlas, right? Ask the algorithm to create some prototypical appearances of every possible tumor it learned to see. And what we were left with is really the first completely AI-generated curation of brain tumor appearances of every specific type of mutation that we're interested in. So these are, again, features that are completely learned by the AI system on its own. All right, so with that, that's pretty much all I have here. The summary is very simple. to create these tools, you really just need to think about what the technology is able to do and whether you have data to answer that problem, and whether there's an easy path to get that tool into clinical practice. And these are just, again, a few of the categories of applications that you might see. So this is my contact information. I think, do we have time for questions? Or I don't know what that is. But anyways, I thank you for your attention. And yes, please let me know if you have any thoughts.